Okay, so in this section we are talking about linear approximation, and this is sometimes called tangent line approximation as well, and that is because we are going to be using the tangent line to approximate values of the function. So we know that when a function is differentiable at a point, we can write down the equation of the tangent line. I haven't yet given you this formula, but if we have a general point A, the equation of the tangent line is going to be f prime of A times x minus A plus f of A. And now notice that this is the slope, and this is just our point slope form, but I've moved that f of A, that value of y, to the other side, right? And so this is the same thing that we've been doing this whole time. Now here we have in this picture a function graphed, so that's the black curve, and then we also have the tangent line at this point graphed there as well. And so you can see that if you were to evaluate the function at some point, we'll say b over here, well, its value would be right here, and then the value that lies on the tangent line is really close by. So the error between the two, or the difference between the two, is really small. And so we're going to use this fact that the tangent line is really close to the function when we are close to the point of tangency, and that is what we're going to use to approximate values of the function. Okay, so this is, in this first picture, we're sort of zoomed out a little bit. In this next picture, we've zoomed in a little bit more, and we can see that the tangent line is hardly distinguishable from the curve itself. So when we really zoom in, it really is a good approximation of the function. Okay, now the idea of the linearization is that, as we've said, the value of the function is approximately equal to the value of the tangent line when x is near a. So just to write this out in math, so using our formula that we wrote down up here for the tangent line, I'm just going to write that in. Great. And this is when x is near a. Okay. So if x is not near a, then it might not be a good approximation of the function. And so you could think of a situation where that would be the case. Like, say you're trying to use a tangent line to approximate a value of the function that is way over here. Obviously that is not a good approximation, so it really is for points that are near that point of tangency. Okay, now the linearization of the function f at the point A is really just the tangent line by another name. So it's just L of x, that's what we use for linearization, and this is just equal to the equation of the tangent line, like that. Okay, so all we've done is take our formula up here and we replace the y with L of x. And so what we're going to do when we use the linearization to approximate points is we're just going to plug them in for x, and then we'll get a value out. Right, so we'll see this in the example. Okay, so here we're asked to find the linear approximation of the square root of x at the point a equals 9 and use it to estimate the square root of 9.1. Okay, now notice that the square root of 9.1 is just f evaluated at 9.1, right? If we plug in 9.1, that is the square root of 9.1. And so this means that we're going to use the equation of the tangent line to approximate the value of f at this particular point, right? So the first thing we need to do is find the equation of the tangent line. So we just do this in the same way that we've been doing it. And so we start by taking the derivative. So we've done this one enough times that I'm just going to skip the part where I write it as x to the 1/2 and use the power rule. So the derivative is 1 over 2 root x. And then we need f prime evaluated at 9 because that is the point where we're trying to find the tangent line. And so we just plug in 9 and we get 1/6. So that's the slope of this line. We are given the x value, but we are not given the y value for the point, so we have to plug 9 into f to get that, which is just 3. Okay, so our slope is 1/6 and our point is 9, 3. And now we just write down the equation of the line. So I guess I'll do this in 2 steps. We will do y minus y1 equals m times x minus x1. And then just moving that 3 to the other side, we get an equation for the tangent line. Okay, and then to find the linearization, as I said before, we just replace the y with L of x. And we get this. That is our linearization, or linear approximation. Those are interchangeable. And so all we have to do is we want to use this to approximate the square root of 9.1. As I said, we're just going to plug this into our linearization. So that means evaluate L at 9.1. Right? And so this is going to give us an approximation of the actual value of the square root of 9.1. And when we do this, we get 9.1 minus 9 plus 3. And then we can simplify. That is just times 0.1 plus 3. And then I guess if we want to simplify it all the way down, we would get 3 is equal to 180 over 60, so 181 over 60. Just once that's, so this is going to be the approximate value of the square root of 9.1, and so that is our answer, half of it. So we found the linearization and we found the approximate value. Notice that 9.1 is near 9, so it does make sense to use this linearization to approximate this value. Okay, now it might seem silly to have done this because we can just plug 9.1 into a calculator and get a value for it, right? But that's not really the point of this, although the problems that you're going to get are going to be probably similar to this one. The idea, the overall idea here is really useful, actually. So what we're doing is we're taking a function that may, behave somewhat crazily, but it is differentiable, and we're assuming it's linear, at least close by this point of differentiability. And so linear functions are very, very nice. They're almost the nicest types of functions we could ask for. And so in some situations, using a linear function can be so much easier than using the equation of your actual function. And if all you need is an approximation, and that's good enough, then it's a good idea to use a linear function. It can really drastically improve your computing time if you are computing something. Or sometimes you might have just a data set and you don't know the value of the function. You literally cannot just plug it in to your function because you don't know how it behaves in between data points, right? So this is a really useful idea, and that's why we're doing this. Okay, so we have one more example that we will do in the next video.